So how do you use these standard reduction potentials? Remembering that half cells are measured against reference cells, this being the hydrogen half cell which has been given a standard electrode potential of 0 volts. But that's not really true, but it's our reference. Using this, they have developed standard reduction half reactions at standard temperature and pressure. But simply, the energy required to reduce these metal electrolytes in 1 mole per liter solution with its electrode against a hydrogen half cell. So looking at a solution of sodium, if the ion is to gain an electron to reduce the sodium metal, it requires 2.71 volts if paired with a hydrogen half cell. Think of it this way. Let's say sodium ions were able to be reduced from the solution to form sodium metal. Our understanding is that sodium, being an alkaline metal, reacts violently with water, which is part of your solution, to produce sodium hydroxide. That is, it really likes to give up an electron. So logically, to force sodium ions to accept electrons requires loads of energy. Take a look at the ever so popular zinc-copper couple. It contains zinc and copper electrodes in solutions of matching ions. Since this is a redox reaction, in order for something to gain electrons, something else has to have lost it. But which half cell is the reduction reaction? A simple technique is to consult your trusty standard reduction potentials. Half reactions with a more positive standard electrode potential mean it has a greater tendency to gain electrons. That is, it's more likely to be reduced. So, copper is more likely to be reduced. Therefore, zinc must have been oxidized. But since the table shows its reduction reaction, we must reverse the half reaction, as well as the sign of the E value to represent the oxidation of half reactions. The total cell voltage is simply the sum of the half cell E values. This means that under standard conditions, the cell will produce a voltage, technically an electromotive force or potential difference, of 1.10 volts. Let's try another example. A copper and iodine couple. Copper is as usual, but an inert platinum wire suspended in a solution containing both oxidized and reduced versions of iodide. Remembering, the electrode is not involved in the chemistry of the cell, it simply serves as a pickup for electrons. Consult your standard reduction potentials. Copper is here. Oxidized and reduced versions of iodine solutions are here, meaning iodine is more likely to be reduced. Therefore, copper is oxidized, so we flip it, producing an overall cell potential of positive 0.28 volts. In this example, the copper half cell is the anode, and the iodine half cell is the cathode. Electrons would flow from the copper electrode towards the platinum electrode.